So you have 10 minutes per presentation. So I will give you 2-minute warning before the end. Okay. So let's start.
Good afternoon, professors. I am Kwan. This is Lo and this is Wen. We are from Wong Secondary School. We are team 18884. Next, we will first introduce some terms and definitions. This is a regular polygon we will focus on, and it is cut along radii. This is a one-portion paper, and the cone made from it is an N1 cone. Its maximum capacity is denoted by Vn1. This is a three-portion paper, and similarly, the cone made from it is called an N3 cone, and the maximum capacity is denoted by Vn3. In general, we will denote the capacity of an NK cone by Vnk. Our problem is how to cut a regular n-sided polygon in order to obtain the greatest total capacity. We will first investigate into the case of a circle because it is a limiting case with infinitely many sides. Its result is also useful in the main problem. Suppose we now have a sector with an arc length x and radius 1. Its capacity can be expressed in Vx, and it will attain maximum when x is 2^6^3 by differentiation. But if we use the remaining sector to make another cone, the total capacity is still not the largest. So we will set a function f2 pi in order to find this greatest total capacity. By differentiation, the total greatest capacity corresponds to the root of this degree 7 polynomials equation. But since f2 pi is symmetric about x is pi, so we can adopt a suitable substitution in order to simplify this equation. And by solving, we know that the greatest total capacity corresponds to at the moment when x is 0.648 pi. And now, we will come to the problem of arbitrarily many cones. Our objective is to compute this expression in order to have a greatest total capacity. We once used Lagrange multipliers to compute this, but it turns out to be very difficult to handle the case. Instead, we find with elementary calculus that two cones are the best. This important result will be included in the following combining theorem. Suppose we now have a k which is smaller or equal to 2^6^3. This sector can be folded into a large cone or two smaller cones. The combining theorem states that the greater cone has the larger cone always have a greater total capacity than the two smaller cones. And now, if we have a sector which is, if we have a circle which is cut into 5 sectors or 3 sectors or above, we notice that the smaller two sectors have the sum of arc lengths that is smaller or greater or equal to a 2^6^3. And we can adopt the combining theorem, combine these two sectors. And we will repeat this process until we have 2 sectors left. That is, two cones are the best. And now we will prove the combining theorem. It is sufficient to prove that Fk attains its maximum when x is 0 or k. And by symmetry, we need to prove that Fk dash is negative or equal to 0 when x is below half k. Now, we'll first check some boundary cases. Then we'll prove that Fk dash is indeed convex. This will require us to check that whether the second derivative of Fk dash is positive. But we can show that the third derivative of v is strictly decreasing, because the fourth derivative of v is always negative. And now we have completed our proof. And the two cone problems and the general problem has been solved. That is, two cones are the best. And now we will come to the problem of a polygonal cone. Since the water inside may be in the shape of a slender cone with an elliptic base, the capacity is expressed in this way. And here, h is the minimum set coordinate of the cone rim. We will parameterize the cone rim in order to find this h. First, we will introduce a coordinate system, where the x-axis is the projection of the cone axis. L is the projection of OH, which makes an angle of beta with x-axis. And phi is the angle between z-axis and the cone axis. It is also the slanting angle of the cone. Principal rim is the portion of the rim which we will parameterize. It is also the rim between the cone axis and the x-axis. And the z coordinate can be expressed in the following way. For a given orientation fixed by phi and beta, z is the minimum value of z is the water depth in V. But we have to first reduce the number of variables in order to do an optimization problem. Notice that a set is dependent on beta, but phi is not. So we will first maximize the water depth with respect to beta first. And it turns out that the maximum of set mean occurs when beta is power k. And now we'll prove that beta is power k. We can prove that if theta minimizes set, it is non-positive. And now, if we have a blue line which corresponds to the cases for which power k is the beta, and the purple line is the other beta that is smaller, we will further assume that set is the minimum at some point A. We can find a path ABO such that set is decreasing. And even the set value at C is smaller than that at A, let alone the actual minimum value on the purple line. So we now have proved that set mean is the maximum when beta is power k. And now we will further reduce the number of variables to 1. For all phi, there exists a curly theta, such that set is the minimum when theta is this curly theta. Phi is a function of this theta and phi. Although theta is a function of phi, but it is so hard to express theta in terms of phi. So we will make use of this bijective relation we can prove and write phi in terms of theta instead. And after some calculations, we can show that the maximum capacity of an NK cone is denoted, can be expressed in this expression in red. And the water inside is in the shape of right circular cone. And for k is 1, the water inside may be in a slanted position, is in the shape of a slanted cone. And this can be found by solving equation 1. This will be also useful to our later discussions. And now, how should we cut the polygon in order to obtain the greatest total capacity? Indeed, for large enough n, 2 cones are still the best. We have a polygonal combining theorem. If we take a portion which is smaller than 2/3 of the polygon, the maximum total capacity is attained when it is not further divided. And if k is not 1, water inside the NK cone is in the shape of a right circular cone for maximum volume. So if L is not 1 or k minus 1, we will immediately have this inequality in red by combining theorem. In order to check the other two inequalities to justify our claim, we will introduce another function, Bn, because Vn1 is so difficult to express. So we use Bn for an upper bound for comparisons. Bn corresponds to the volume of the filter cone when the highest point and the lowest point of the rim is on the same level. Now, using this Bn, we can easily check the third column. And with the help of mean value theorem and convexity, we can also check the second column when n is 6 or above. For the missing cases, we will use some manual calculations done case by case. And now, our polygonal combining theorem has been justified. That is, for a paper regular polygon of 3 or more sides, 2 cones are still the best. But triangular paper is the only case which involves 3 cones. If the polygonal paper has more size, we can compare the two expressions in different color in order to obtain the greatest total capacity. Here is a summary for our results. But after the submission of our project, we further investigated the slanting angle for which the cone's capacity, the capacity of the cone is the greatest if it is made from an isosceles triangle of vertex angle gamma. Here, we will put gamma is 2 power n, for which n is an integer, a positive for which n is a real number, which is greater than 2. We can assume that V is the maximum, that is the capacity is the maximum at a slanting angle of phi, whereas the water depth is obtained when theta is this curly theta. We can still use theorem 14 because these results do not rely on the assumption that n is an integer. And we have a theorem that after doing many calculations, we can find that gamma over 4 is a very good approximation to phi. This is impressive because we know that if we want to have this phi, we need to solve the equation 1 I have once mentioned. And this is very difficult with the very difficult with the introduction of Chebyshev polynomials. So this theorem provides a very good approximation to phi. And based on the results, we can also prove this. And this is the end of our presentation today. Thank you.